So
it's not we talk about Boomerang subalgebra, Boomerang algebra.
thank you for the invitation. This is not ongoing work with the Yai. One is Yai Hartmann, the other is Yai Glasser and Yongle from China. So I'll just briefly. So this is for me is a countable. And this is time for the talk. So the first story that comes from this topological side of things. That so to group gamma we can associate some gamma. This is the collection of all states. And as he told us, this is compact and metrizable with the Chaupory topology. One easier way to see the Chaupory topology is to think that is to give it the topology from 0, 1 to 0, 1 to the power gamma. So in particular, I would say that Hn converges to H in this Chaupory topology, if and only if the characteristic function of Hn converges to the characteristic function of H pointwise for each G in gamma. This is precisely the product topology that is induced from 0 to power gamma. So in particular, it converges, Hn converges to H for every H in H. There is some and not after which it is in Hn. And if there is some H for which it is not in Hn for after some point, then it cannot converge. That's exactly what the topology is. Okay, and then I have a nice action of my group gamma on some gamma. So when I say an action, this means that I have a homomorphism from my group gamma to the homeomorphisms of sets of gamma, and maybe I write it here. So that from gamma to the homeomorphisms of gamma, where I think so phi g of H is just G inverse, the conjugation action. So G inverse is again a subgroup, and this is nicer, and this is continuous with respect to the Chaupory topology. That is there in the beginning. So I'll just ignore, abuse the notation, and I will not write phi and all that. I'll just say G dot H is GH G inverse. Just because I can. Okay, and then so once I have an action, so this is a compact metrizable space. I have an action. What I can do now is I can look at the collection of all invariant. So this is the definition: invariant random subgroup. So this is a gamma invariant probability measurement on sub gamma is called an IRS. IRS is the short form for invariant random subgroup. So when I say gamma invariant, it is invariant with respect to this conjugation action that I have up here.
So it's measured, it's called the subgroup.
Exactly, but it is not actually a subgroup. It's just the way of saying it.
When you say you mean like a Borel measure with respect to this?
Yeah, it's a probability measure, Borel probability measure, with respect to the topology that I have here. Now, what is an example of such a thing? Because the legal example is the delta major of normal subgroup. Right, because the normal subgroup is invariant with respect to the conjugation, so delta major would keep it. This is invariant probability measure there. Now here is a non-trivial example. We'll come back to another one in a minute. So say I have an action which is measure preserving in the sense that Gm is M for all G in my group gamma. So the measure is actually preserved in the sense that if I translate this measure by the G, this does not see the difference. So M of G inverse C, basically what I'm saying is that M of G inverse M is same as M of F for every function. So there is no difference between the measure doesn't see the difference in the action. So now I have a nice map. So I can define a map. This is what is known as the stabilizer map. From X, in the connection of subgroups here, we sense each X here to the fixed point subgroup, which is basically all those group elements that fix this point. So I send X to gamma X. And this map start is measurable. It's actually it's continuous really. So measurable with respect to the topology here and the geometry topology here. And the second thing is that this is gamma equivalent. In the sense that star of G dot X, which is by definition gamma of G dot X, but it can be checked that which is exactly G gamma X G inverse. Yeah, because if I'm fixing Gx, then I'm comfortable here, and the vice versa is also true. So this means that what I can do is I can push forward this invariant measure that I had here to get another invariant measure here. So this is what is known as the push forward measure, right? Given any two maps, so this is true in general. If I have a map, let's say T, this is a measurable map. This is measurable. Then P star of n is again a probability measure, given this is a probability measure, and this is defined exactly. You just put it back and give it the measure and here. This is what is known as the push forward measure. So, and if this map was equivariant with respect to the action here, this would be equivariant. So, in particular, star of n is an invariant random subgroup. So it is a gamma invariant probability measure on the connection of all subgroups. And moreover, this is a theorem about Grassner and Invariant that every IIS they used from forward of a stabilizer map. In particular, if you give me an IRS, I can always find a probability measure preserved in space XM such that that IRS is exactly going to the push forward of this map. So there are no other invariant random subgroups but this particular example. These are the only invariant random subgroups that are there. Okay. But I mean, so why, so now, okay. So another, I'll finish this section with another theorem, which is very well known. This is a very special case of Margolis normal subgroup theorem. Of course, this theorem is true in a greater generality, but I'll just take it in the groups that I understand. So let's take gamma to be a certain G. And n is bigger than equal to 3. So then Margolis shows that every normal subgroup in my group is either finite or has finite index. This is somehow a classification of all normal subgroups in my SNNG.
What's the index again? Of the sub, what's the an index of the subgroup?
So index of a subgroup is so this is this thing, right? So this is basically, so if I have a normal subgroup, so gamma on n is again a subgroup, right? So basically this is finite. That's what it means.
Oh, okay. the number of cosets.
Now number of cosets are finite. So basically he said that either my group is finite or it has the number of cosets are finite. But so this problem just trying to motivate how Boomerang came into the picture. So what Glasser wanted to do was to go beyond the normal subgroups. So he wanted to ask if this theorem can be proved for some other bigger class of groups that are not necessarily normal. So then what he did was he introduced the notion of a Boomerang subgroup. Basically along with one of his postdocs. So a subgroup H in sub gamma is called Boomerang. If for every group element, I can find an increasing sequence of natural numbers such that G and I H G minus Ni converges to H in subgroup of H. In particular, if I keep on conjugating them, at some point of time, I'm going to return back to. So basically, given any neighborhood of H, I can find some sequence, something like that, such that G and H G inverse is going to be in that neighborhood after some point in time. And that's why he called it Boomerang, and it keeps returning back. So in general, more generally, in the topological dynamics, there is something called a recurrent point. So let's say I have a transformation from X to X. X is a topological space, T is any continuous map between them two. So in X is called a recurrent. If for any neighborhood U containing X, I can find some any link such that T and X is again unique. So basically T and X converges to X as n goes to infinity for some subscript. And exactly what the Boomerang tells me is that this subgroup is a recurrent point with respect to the conjugation action. That's what this definition tells me. Now, what is an example of such a thing? There's it here. Of course, not much of them. Because G and H, G inverse is again H itself. And the second is finite index subgroups. This is not difficult to check that if I have a subgroup which has finite index, then it is also going to be Boomerang. But more non-trivial example, perhaps this most interesting part of this is that if I take an IRS, every invariant random subgroup, we call that IRS is an invariant and probability measure. This is supported on Boomerang subgroups. So if I have an invariant, if I have a gamma invariant probability measure on the collection of subgroups, then it only sees Boomerang subgroups. It doesn't see, so any other subgroup has measure 0 in my thing. And why I define this as true? Maybe I'll just illustrate the proof. This is pretty straightforward. So there is something called Poincare recurrence theorem. In topological dynamics from the time of Poincare. So what it says is the following. Let's say I have again a topological space and M is a probability measure on it. And T from Xn to Xn is a measure preserving transformation in the sense that is such that T star of n is m itself. So when I push forward this measure by T, I get the measure itself. Then Poincare is shown that then m almost every point in X is recurrent with respect to T. So this means that there is a cone offset here, so that every point in there is a recurrent point. The recurrence is in this sense. So now what I do is I do it pointwise, and my countability of the group comes into the picture. So what I do is I fix S in gamma, and I define Ts from sub gamma to sub gamma, and I send H to S is the conjugation. So if I have an IRS, so if mu is an IRS, particular, this is invariant with respect to the group fraction. So then Ts star of mu is mu itself. Because my mu is invariant with respect to this conjugation action. So by concurrent recurrence theorem, I can find some Fs inside sub gamma such that every H in Fs is recurrent with respect to the conjugation action minus.
So by cone you mean length? So,
By cone null, I mean the complement has nulls. Complement has measure 0.
oh, right. Yeah.
So I found a measure. If I find a non like a measure one subset here, so that every subgroup in there is recurrent with respect to just this fixed S. But I am in a countable setup, so I can intersect these lines. This is still measurable. The measure of this guy is still 1. And if I pick every element H here, so every H in here is going to be boomerang or recurrent with respect to every element. This is exactly basically shows that every IRS is going to be supported on boomerang subgroups. And note that the Poincare recurrence theorem does not necessarily use the compactness or anything, it just needs an invariant measure. And then we'll come back to this later when we talk about subalgebras. So the moral of the story is that if I take an invariant probability measure, it is going to be supported on this boomerang subgroups that they introduced. Questions? Feel free to stop me or. Okay, so. This shows with respect to this boomerang notion that I maybe give it here and maybe write it here. So what the group, which is a Margulis normal subgroup theorem here, so this actually generalizes the Margulis normal subgroup theorem. So they show that every, so you can also gamma is less than mg when you get an equal to 3. Then they show that every boomerang subgroup H inside this sum of gamma is either finite or have finite index. Which is a generalization of the Margulis normal subgroup theorem, because it is for every boomerang subgroup. And of course, they do many other stuff. So what we wanted to do was to enlarge our point of view. Like we have been talking all this while that Aaron told us. So This is where the second part of the story comes. So what we wanted to do was to go towards the group one algebra. And then ask some very natural questions. For example, so L gamma I don't need to define again. Like I have said, there is a natural map from my sub gamma to the collection of subalgebras. So when I say subalgebras, I mean the fundamental subalgebras. And this sends the subgroup here to the corresponding group one algebra. This is a very natural map. So now what I do is I equip sub gamma with the Java topology. And here I give it a first Mariester topology. Of course, we know that this map is not onto because there are many subalgebras here which do not come from subgroup. But the first natural question is this map continuous? Like, can I see this subalgebra of L gamma as a big and enveloping thing of this sub gamma? And this is exactly what we do. So this map L is continuous. Right, and in the left hand side, I have the Java topology. On the right hand side, I have the first Mariester topology. So the sub gamma sits nicely inside the subalgebras of L gamma. So then the question that we wanted to answer is, can we find some connection here? Connection inside the subalgebras of L gamma for which the map L is onto. So in particular, I want to pick a subalgebra and I want to show that it actually comes from a sub.
Questions?
Yeah.
I guess it's not known whether that map is injective, right?
This map?
Yeah.
I mean, canonically it is injective, but if you are asking isomorphism, then it may not be the case.
Oh, okay, because I thought like for free groups, it's not known whether their group phenomena is isomorphic, right? So
Yeah, but this is isomorphic. I mean, yeah, if you ask isomorphism questions, then it is not known. But if canonically, then there is.
What do you mean, sorry?
So you can just think that if you say L of H1 is exactly L of H2. Like, I mean, not necessarily with respect to the isomorphism. Yeah, exactly. Yeah. Just inside the group one algebra itself, not as an isomorphic copy, then H1 and equal to H2. But if you ask isomorphism, then it is not necessarily true.
oh, okay. Yeah, thanks.
And this is exactly one of the problems why we introduced this subject, to see if we could do something, but it turned out that we cannot. But maybe I'll come back to that. Okay, so L is continuous. So now, so we wanted to answer this question, that if I pick a subalgebra, when does it necessarily come from a subgroup? Okay, so maybe okay. So before I go there, so there is a nice. So now what I can do is, since I have an across Mariester topology here, I have open sets. I have a measurable collection of sets. So I can pretty much do a generalization of this IIS here and ask for a gamma invariant probability measure on a collection of these subalgebras. And that's exactly what we did in definition. Invariant, we call it invariant random algebra. So this is a gamma invariant probability measure on the collection of all one-dimensional subalgebras of N gamma, each called an invariant random algebra. Is there a question?
No, that's just.
No, it's sure, I'm Irish. It's music. Can you remind me what's a non-trivial example of an IRS?
of an IRS?
Yeah.
So basically, we can take any measurable action on this thing, and then we just push it for another stabilizer map, and that gives me a non-trivial IRS.
Right.
And from that question, actually, that gives us an example of an IRA, because this map is continuous and it can be shown that, okay, maybe I should say, I didn't say how the action was. So there's a natural action of gamma. Yeah. Sorry. So there is a natural action of gamma on the subalgebras. It's the conjugation action. So G dot M is just lambda G M lambda G star. The conjugation on the with respect to the subgroups just translates the conjugation here. So now what I can do is I can given an IRS. So if mu is an IRS it's an invariant probability measure, then the push forward by this map L is actually an IRS. And another trivial example is delta of M, where M is invariant. Right. So if M is invariant with respect to this conjugation action, then the delta measure supported on this would be an IRS. So what is an example? Maybe I'll just this should lead us somewhere. So an example of this. So for example, we can take A to be the N, where N is a normal subgroup of 5. Right, and since this N is invariant with respect to the conjugation of group action, it is easy to it's actually possible that this thing is actually N of N. Because I'm conjugating, I'm still inside my normal subgroup. Right, because I mean, so how is this defined? So this is, as Aaron told us, this is basically the span of these lambda h's, where h is in N, and I close within this of the point. Right? Now, if I do the conjugation at this level here, so for each G gamma, the span of lambda G, lambda H, lambda H star, as H in N, this is again going to be inside this thing. Because this is precisely lambda G H G in. And then if I look at this SOT closure here, SOT closure, I get what I want. Yes, I have an example. So actually, I'll come back there now. So now. So the first step to understanding this question was taken by Neumann, and along with one of his PhD students, they proved the following. So take gamma to be SLNG, where n is greater than or equal to 3 and the center is trivial. Then they showed that every gamma invariant subalgebra M inside my group on given algebra is actually of the form L of N. or some normal something. So in this case, in these groups, there are no other gamma invariant subalgebras other than the ones coming from the normal subgroups. So these groups are very, very basic in this sense. So in particular, if we focus here, so what they showed was that if I have an IRA which is supported on a delta measure, then those IRAs are actually coming from IRSs. They're actually pushed for some IRS which is supported on this end.
This is what you've written that the center is trivial, that's just an observation, not a.
Sorry?
This center gamma is trivial, that's just an observation you're making?
No, that's not observation. Right, because in SF4G I have something in the center.
Oh.
I want the group to be very non-amenable. So this actually motivated because these are very rigid groups, and then we wanted to know if there are other groups that satisfy this property. So we introduced this notion of invariant subalgebra rigidity. We abbreviated as IFR. So gamma is said to have ISR property if every gamma invariant algebra M is of the form L or some numbers. So there are no other invariants of algebras other than the ones coming from the normal subgroups, and this is an example of this such a thing. And then we wanted to ask if there are more groups that satisfy this property. And together with Yogle, we are able to prove the following. So take gamma to be non-amenable, like you define it, non-amenable hyperbolic groups. Or a product of such groups. That would be finite product. Then gamma arch particularly gamma invariants of algebra here comes to numbers. So an example of such a thing basically, let's take Fn, the free group on any n generators. So do you want to define a non-amenable group or is it fine? Or?
I think probably some people don't know really.
Okay, so an amenable group definition. So we look at A infinity gamma. So these are all those functions from gamma to C, such that the supremum of f of s is 5. Okay, and then there's a natural action of my group gamma on A infinity gamma. So for S in gamma and F in A infinity gamma, S dot F at any point just simple by inverse. So gamma is what I'm here. If there is a state P from L infinity gamma to C, such that P of it is inverted, it's inverted for all L infinity gamma. So this is basically saying that there is a gamma invariant mean on L infinity gamma. An example of amenable groups are all abelian groups, solvable groups, and this is a very non-amenable group. Okay. So, is there a group that does not have the ISA property? Here is a stupid example. It's actually stupid in that sense because. So let's look at gamma G mod PC. These are the tables. So when I look at M, the sum of this form, lambda x plus lambda square C and lambda like P not so A lambda E, where A and C are complex. So what I do is I give them same coefficient for S and its inverse, and then lambda is free. And this is the von Neumann algebra. This is a legitimate von Neumann algebra, and if you product them, it is going to be closed under product and so on. And since this is finite dimensional, everything is fine. Now I claim that it does not come from a normal subgroup. Because if it contained a group element, then if it cannot contain lambdas individually, because then I have to contain lambdas S square as well, and then I get everything. So this M is actually not on the form L of n or any normal thing. Actually, this construction works for any element, as long as I have more than 3 elements. So actually what I'm doing is, so there is a homomorphism, right, from G mod to Z to Z mod to Z. That sense is right. So this actually induces a homomorphism from L of G mod to Z to L of G mod to Z. And then I'm just looking at the fixed points of this feed data. So this M is actually L of 0 G feed data. So all those elements in my group von Neumann algebra which are fixed by feed data, like the fixed point algebra. I have 10 more minutes or yeah. Okay. So now we have ISR, we have so maybe okay. So here, so after this result, actually this has been generalized by recently by Yoraki Silas and been soon. So they have actually showed it for many more bigger class of groups. So they have shown it for something called asymptotically hyperbolic groups. And again, non-running group. So these are bigger class of groups. And they have shown that each such group gamma has isoprotect.
What's the first? It's
Sorry,
the first way above how tall it is.
this is the syndically hypothetical.
Asymmetrical.
What's that mean?
I will not ask you the definition. It's a very complicated. So basically, what we suggest is that there is a topology. So Rn, for example, closed the group ring with respect to this strong operator topology. Instead, what I can do is I can close this group ring with respect to the norm topology on B of A, right? Because I have a topology there. And what I get here is this is known as the reduced group system. So this is basically this is a non-closed star algebra. And we said that gamma is C star simple if this reduced group C star algebra is simple. In the sense that does not have any non-trivial closed ideas. Okay, and an example of such a thing, if all these groups are examples of such C star simple groups. So free group, even all these are syndically groups which are non-amenable, these are all examples of C star simple group. Even SN and G for n bigger than or equal to 3, these are all C star simple groups. So maybe there is this somewhere there is something very something else going on behind the scenes that possess this higher property. Maybe this is true for all C star simple groups, we do not know it.
It's this, what H and bar, this is,
So this is a free group, so
oh,
free group around n generators and n is given in equal to. So now we come to the Boomerang subalgebra. So of course, with all this we know naturally what the definition should be. So this is Boomerang subalgebra. And of course, why did we want to do that? Because we wanted to ask if we could prove ISR this sum that if I pick a subalgebra, when does it come from a subgroup? Can we extend this for some subalgebras which are not gamma invariant? And this is where we introduced this Boomerang subalgebra. So M is called Boomerang. If for every G in my group, I can find an increasing sequence such that lambda G and I M this converges to A, and again this is in across minus algebra. So in other words, this M is a recurrent point with respect to this across minus algebra. So M is a recurrent. And of course, the proof that we did for IRSS would suggest the following. That an example of course in invariant subalgebra is going to be a Boomerang subalgebra. And second is that every invariant random algebra is going to be supported on Boomerang subalgebras. is exactly the thing, the Poincare recurrence theorem, because I don't need the compactness of the space. And then we basically asked if we could prove that the Boomerang subalgebras are coming from subgroups, if that can be shown for a class of groups. And that's exactly what we have proven so far. So gamma is again a illusion-free, non-amenable hyperbolic group. The causality means that I do not have any finite elements other than the then every Boomerang subalgebra is actually of the form L of H for some sort. And paired with this observation here, what it says is that if you give me an invariant probability measure of the connection of subalgebras, and with respect to this measure I pick a subalgebra, then this subalgebra is necessarily going to come from a subgroup. So with respect to certain randomness, we can always find that the subalgebra is coming from a subgroup. That's exactly what it says. I will stop it. I will put it back.
Do you have any questions?
You mentioned that the group sees the algebra, and I guess you could develop all of this.
Yeah, the problem is the topology. The Efrat-Maritan topology does not necessarily go to the group system algebra.
So this topology is pretty opaque.
Yeah, so basically there is this notion of convergence topology, and this can be done for any collection of closed subsets. So Efros actually showed in 1960s that if you give me a topological space and you consider the collection of all closed subsets, there is actually unique topology on it. And this is which makes it metrizable and compact, and this is the convergence topology. And this is exactly the Efros-Maritan topology, is exactly the convergence topology that comes from this thing, because the unit ball is weak operator topology compact for any polynomial algebra. So you look at the collection of all polynomial algebras, you look at the unit ball there, these are all weak operator topology compact. You give it the convergence topology, and this exactly is the Efros-Maritan topology.
So you can't do something.
You can exactly do that in these two stage algebra. That is clear. But maybe there's some other way. I don't know.
Because there is a component of IRS in the topological setting that's.
Yeah, this is URSS.
Subgroup, right?
This is uniform recurrent subgroups. The problem is again that you need compactness, and this Efros-Maritan topology is far from being compact for any reasonable group.
So in the last year, maybe you said this, but so can you characterize when the subgroup is normal?
Is what? Sorry.
When the subgroup is normal, like can
Yeah,
you say the subgroup is normal if and only if the subalgebra is something?
Yeah. I mean, the subgroup is invariant if and only this subgroup is normal.
Oh, okay.
And of course, I mean, this subgroup is Boomerang if and only this group is Boomerang in the sense in the original sense.
Also a question, I'm not sure if it's that meaningful, but so if you look at the group algebras or the finite groups, I guess they're also compact quantum groups in the sense of
Yeah, you can.
knowledge, huh?
Yeah, maybe you can go for compact quantum groups, but I am not an expert.
I think finite, yeah.
Yeah,
Well, I think
it's finite.
quantum calculus will be always locally compact quantum groups.
Right, so my question for this is that, okay, so now if you quotient by a normal subgroup, I guess we'll still have a locally compact quantum group. But now what happens for these Boomerang subalgebras? Do you still get some compact quantum group or something like this, or do you leave? So is the co-product something?
I mean, another question you could ask would be like if you allow for compact quantum subgroups or like instead of just subgroups.
Right, so the question is
like,
kind of.
yeah.
Yeah, I mean, we have to first make sense of invariance there. I mean, this invariance is, I mean, maybe with respect to co-product, I don't know.
Okay, sorry.
No. You know, but also there is a natural question with respect to the group system algebra. Like if you pick an invariant subalgebra, does it necessarily come from a normal subgroup? That is not known. Because the main problem is the existence of a conditional expectation that does not hold true.
Because there's now like sort of there's a notion of rigidity of groups, which is like the groups are isomorphic only if their one algebras are. Which is not going to happen in any nice cases like immutable or whatever. But there are results that show that you might have a group, one algebra that's like rigid in a group, theoretic sense that it has to come from like if it comes from a group Caesar algebra, you know it's going to be exactly that group, but it might not be quantum group rigid. So my question would also be like, how does this relate to that notion of rigidity? Like, obviously you have groups that are we don't know whether or not they're rigid or not.
But I mean, we have actually examples. For example, in infinity. So S infinity is an amenable group.
Oh, that was my follow-up question.
Yeah, S infinity. So S infinity is actually the union of these things. So this is an amenable group, but by Cohn-Shirley theorem, we know that L of S infinity is actually isomorphic to this Lamplighter group. This is what is the Lamplighter group, and this does not have the ISA property.
Well, I suppose it's isomorphic to any of them.
Yeah, anyway, so but this doesn't have ISA property. So that's exactly, I mean, we wanted to actually try to approach the Cohn-Shirley problem by using this, but this was basically, we couldn't, I mean, because basically once you prove that this has ISA property, nothing could be done about it. So hyperbolicity is used because for any hyperbolic group, I have a natural function on the corresponding group of boundary. And for every, and we know that for every S in gamma, there are exactly two fixed points here, such that S actually fixes them. And if n y converges to xs plus as n goes to infinity for all y not equal to xs minus. This is what is known as the North Pole South Pole property. So we use this property to somehow show that if I pick an invariant of algebra M, then I know that there is a conditional expectation here. EM. So use this to show that EM of lambda S must be inside the cycle of S itself. And then we basically play the game from there. So what is important? So you need to show that M is actually coming from a subgroup. What is important is to show that EM of any group element is actually a constant multiple of itself. So when I project my group element via this conditional expectation, I either get the group element or nothing. That's exactly what this means. And then you look at all those elements which are basically projected to itself, and this is my sum. That's the idea behind this thing. And this is exactly the reason we cannot do this for the group C algebra, because there are no conditional expectations.
I have another question about this relation to C star simplicity. Can you say any, like, I mean, because it seems very strange to me that something of a C star property would pop out of this.
Yeah. So basically, so
Stuff.
maybe I'll right here. So even though we this sub gamma seems to be very topological object. So just to go back to the recurrence algebra setup. So we have a natural map, the canonical trace from C r star gamma to C that sends the corresponding group element to 0 if it is not identity and to this identity. Right? This is the canonical trace. So actually what I showed is the theorem shown by Kennedy. That Kennedy is shown the following. Of course, there are many other people like Yair and so on. So they showed that gamma has unique trace property, which is basically saying that the canonical trace is the unique trace on the group C algebra. If and only gamma invariant probability measure on the collection of subgroups is the delta measure at identity. So this is amenable values. So the collection of all amenable subgroups inside my subgroup is closed in the Algebraic topology, and you look at all invariant probability measures there. So gamma has unique trace property if and only the amenable subgroups in the only probability measures there are the probability measures supported in identity. And similarly, gamma is acceptable if and only the URSs, so these are the uniform recurrent subgroups, on these amenable subgroups is the identity. So there is some sort of connection between the collection of all measures here and URSs here with respect to theta simplicity and so on. So I'm not surprised that this pops up here, but it's not clear to me how this is relevant to the discussion.
Any further questions? If not, let's think. There's no contact.